So my talk is two parts. The first one is an advertisement, so you are warned, you can run away. And the second one is an experiment. I'll try to explain, to give you an idea of what you can do with Coq Elpi in a very unconventional way. So either you fall in love with it, as I did, or you run away. But well, let's see. So first of all, Coq Elpi. The first thing is Elpi. Elpi is a programming language that lives on its own. It's not really related to Coq. You can use it by itself, and it implements a dialogue, a dialect of another language called Lambda Prolog. I will try to give you an idea why I like the Prolog part in the second part of the talk. And just I want to remember that to recall that the Lambda stands for some language features that makes it easy to manipulate syntax trees that contain binders, so you don't have to manipulate numbers, the Brown indices, but you can just talk about names, and the runtime does what is needed for you behind the scenes. And the other thing I want to say about Elpi before moving on is that when you talk about a programming language, especially in academia, you think about the language in the abstract sense, but what makes a conventional programming language useful is not just that, it's also the platform that comes with it, the piece of technology. There are languages out there that we don't love, like Python or Java, for example, that are very useful because they come with a solid platform behind. And this was just to say that from the very beginning, Elpi was designed as a language that you should embed into a larger application. And a lot of the energy was put into providing a foreign function interface that would make it easy to expose the internals of the host application to enable to access the data, call the functions of the host application. And when we go to Coq Elpi, I hope you can read something here. It's a plugin for Coq that embeds Elpi and lets you write tactics or commands in Elpi. And it takes advantage of the fact that it's very easy to expose the internals of Coq to Elpi programs. There is some documentation if you're interested in some examples. The main entry point to know what you can do with Coq Elpi is this Coq built-in file that is generated. It's the list of the APIs of Coq you have at your disposal when you write commands or tactics. And okay, two things I want to say about this file. One is that this file is very long, so you have access to many things. And the other one is that you manipulate Coq terms are represented using this abstract syntax tree. And the only thing I want to point out is that you have these funny things here. For example, this is the node for the Lambda abstraction. This is what you would write in Coq. And here you have an argument that stands for the name, the X, an argument that stands for the type T, and then a functional argument that stands for the body of the function. This is what people call higher order abstract syntax. And if you know what it is, this is exactly the language it originates from. If not, well, it's not very important for today, but I just wanted to point this out. And instead of going through the list of all these APIs, I'll just go to an example. So this is a file of mathematical components, and it is a tricky file that defines hierarchies in, algebraic structures, part of the hierarchy that is in this library. And so this is a diff. On the left, you have the current state of the file. And on the right, you have a new version of the file where we use commands implemented in Coq Elpi. Together with Cyril and Katsuhiko, we implemented this little program called Hierarchy Builder in Coq Elpi that provides a couple of commands. And as you can see, what you have on the right is much smaller than what you have on the left. What you have on the left is a long script that starts modules, declares records, another records, coercions, another record, section variables, definitions, notations, more coercions, scopes, canonical structures, etc. And on the right, you have the invocation of two commands implemented in Coq Elpi that actually perform the very same, roughly the same things that are done on the left of the screen. So you have access to all these APIs that let you do all of this from a program written in Coq Elpi. And that's, I think it's enough for the advertisement. Unless you have a question, just interrupt me. And the other thing I wanted to show you is how weird but also interesting LP programs are. So maybe I should make this slightly bigger. Okay. So here is how you define a command in Coq Elpi. First, you begin the command, then you accumulate some text that can come from the script or can come from an external file. Then you type check your program, and then you run it here. This program is a bit silly. It takes in input a term, applies a transformation on it, and imprints it out. Okay. Let's just focus for a second at the main part of the program. This is the entry point. These are the arguments. Capital letters are variables by convention. So here what the system does is that it calls an API to print inside Coq input followed by the term, then it transforms the term T into T1, and then it prints out the result of the copy. So just let's run it to see what it does. Let me clean the output, otherwise it won't be very readable. Let's remember here how the terms are represented. Application of a term to another one is represented with the up node followed by a list of terms, the head and all the arguments. So here you can see that this term is passed to LP as the up, and then here we begin the list. This is the end of the first argument, that is the addition of natural numbers, and then you have two other arguments. First one is 1 and the second one is 2. Okay, maybe I should do something like this to make it a bit more intelligible. Okay. Okay, so now let's try to make to look at this copy term that is the core of my program. This is a declaration of its type. Copy term takes a term in input and produces a term in output. And then the way this little program is written is by 3 rules. Okay, all programs in this programming style are made of rules. And the funny thing to me, the very interesting one, is that these rules make sense on their own. Okay, and we will see what I mean in a minute. I have 3 rules. A rule that says that all the global constants like addition or successor or 0 are mapped to themselves. And then I have 2 rules that explain how to map composed terms. If there is the application of a function symbol to one argument, then we map it to the application of the same function symbol to another argument, B1, that is obtained by mapping A1. So it's just a sort of recursive call over the argument of the function. And if the function has 2 arguments, A1 and A2, well, we generate B1 and B2 with these 2 recursive calls. Okay. So right now the program does nothing. It does is the identity. Okay, it's just doing a silly copy. Maybe we can add a rule to see if we can do something more interesting. Oh, the demo effect. Well, something that you can do is to write Coq terms inside a lambda an LP program by putting them between these funny brackets. So here, for example, I could do this. Whenever we find 1, we map it to chew. Okay. Okay, so as we expect, 1 became 2, and 2, if you think this representation as a natural number, there is a 1 with a successor around it, so it's mapped as well. You can also do something a bit more interesting here than writing full terms. You can, for example, say that if what we find is the successor of something that I call x, so x is again a variable of LP, and this is the syntax to go back from the syntax of Coq, that is between these brackets, to go back to the syntax of LP, okay? And maybe here what I want to obtain is the successor of y, where copy term xy, okay? So this new rule will double all the successors that are found in the input. Okay. So it seems to work. But okay, so the idea of this program is that I'm adding here rules to do something interesting. These rules are there, and this one is what maybe I want to add because I want to implement the double function here, okay? This is not how you would like to work. You don't want to modify programs in their source code. You would like to uh, patch them a posteriori. You would like to add rules on top of what exists. And this is very easy in this paradigm because rules make sense on their own. So what we typically do when we write an NP program is to pair it with a database that can be extended a posteriori. Let me call it copy.db. And let me put some stuff in it, like the basic rules, okay? And then what I say is that my program is now made so the database is one thing, is a collection of rules, okay, like these ones. And now my copy term program is made of the rules from this database plus the text that is below, okay? And so now my program is as the original one, so it does nothing. But I can later on add to the database an extra rule like this one, the one that I had before, and now it doesn't work. It still does the identity, because if you say nothing, this rule is added to the program at the very bottom. Okay, so this rule takes precedence over it. Well, it's easy to fix. What we have to do is to give a name to this, to the first rule, for example, in it. We could name all of them, and here say that we want to put this new rule before the one that is called init. So we put it on top, exactly as we did before, and now our program works as we expect. So the point I want to make with this actually silly example is that the language is designed, the fact that programs are expressed with rules makes the structure very simple, and it's easy to modify them a posteriori and let the user extend your programs by adding rules at the right place. And this is not something that is easy to do if your programming language is, for example, a functional programming language. You can imagine that this program is mainly a recursive function that does a pattern matching over the input, and then you have 3 branches for the 3 rules. But it's not so easy to modify such a program a posteriori by adding an extra case in the pattern matching. Okay, it's not an operation like this one that adds a rule that makes sense on its own to a set of rules. It would be like a textual patch that can be done, but it's not very practical. Okay, while here the language is so simple that adding a piece to it, adding a piece to an existing program is a pretty trivial operation. And that's all I wanted to say. Thanks for listening.
Thank you a lot, Enrico. Any questions about LPA? Any trollish question? I can make him up a few on the spot if needed.
What is Lord and Savior?
The
Is it open recursion? What is it?
Yeah, open
yeah,
recursion.
it is exactly what I'm doing.
Yeah.
But okay, the example is very simplistic. I took the identity function and I'm patching it. But you can also patch something more interesting than the identity function.
So I will be impressed when you manage to perform all the examples by Jason given in his PhD, like gigabytes of terms.
So let me no, there's no such operation for that. You would need to copy paste this code and rename the function. If I understood correctly your question.
But Enrico, can't you also create rules with tactics? I mean, if I remember right, there's some API to call to add a rule which you somehow constructed, let's say in LTAC2 or something like that.
So, I have Coq Elpi1. You can call an Elpi1 tactic with a name, a list of arguments on a goal, and it will give you the other goals. You can, yeah, so yes, but I think that the question of Eve was, can a program manipulate another program and make a copy of this program by itself? And yeah, I mean, it's not exactly easy to do.
Mm-hmm. So, but in normal Prolog, you have that. I mean, you have ways to construct rules and add them to the database as part of Prolog.
Yes, you do. You do have that. We do it all the time in Hierarchy Builder. You can craft a clause and add it to the database or add it locally and temporarily to the running program. In Prolog, it would be assert and I think reset. In Lambda Prolog, you really have an operator for adding a clause temporarily to your program. That's called implication, logically speaking. But today I have no API to ask which are the closest part of a database, give me a list of them so that I manipulate. It would be doable, but not there.
You are now unmuted.
Well, in OCaml, you cannot list the functions of your environment and manipulate them either. If I understood again your question.
You are now unmuted.
Yeah, you can do higher order programming as well. So for example, these two rules are completely silly. What one would do is this. And then just to give you an example. So you have higher order predicate.
I think that if this question boils down to the problem that whether the databases are first order or not.
Yeah. As I said, they could be made first order because you already have the possibility to manipulate clauses. Clauses are just a syntax, so you can manipulate the syntax trees as well. But I don't have an API that gives you a database as a list of clauses. It can be done. We kind of do that because in Yarashi Builder sometimes you have an API in the standard library that is called find all. Okay, you give it a clause, I don't know, foo of X, and it gives you the list of solutions to foo. Okay, but it's not exactly as getting it depends what foo is. If foo is just a bunch of facts, then this is exactly like getting the list of the clauses of your database. If foo is a predicate defined by recursion, then it's a completely different story. So the answer is yes and no. There is no such an API right now. It could be added very easily, but it's not. We didn't feel the need so far. So I hope I answered.
You are now unmuted. You are now muted.
Yes. So far, listing the content of a database, the syntax of the clauses in a database never occurred to us. I think it's doable, but I never had to do that.
I have a question. Do you guys provide any special support for reduction?
Right. So it's on the screen. So you can either implement reduction by yourself. I mean, there is an implementation in Elpi itself of beta, WCAD, whatever. Otherwise, you can call these guys. So the lazy reduction engine is the one of the kernel, called by value, and this would be VM compute. You can also, it depends what you want to do. Sometimes you just want to compare terms up to reduction, and in this case, you can call the unification of Coq, this one.
Yes, I'd be interested in more programmable yet efficient reductions than the ones natively supported by Coq.
Can you be a bit more specific?
Yes.
You would like to implement
a
better simple tactic or something like this? Or?
The use case that I had in mind was simplifying a very dependently typed equality operator into a simpler one that one would write by hand. And if you try to do this manually, you quickly run into this issue of, well, there are some, most constants you would like to unfold, but some you wouldn't. Perhaps the AND function, for instance, you would like to keep as is in the simplified term because that's what you would write by hand. But all the dependently typed stuff you would like to simplify away because that would make the final term much more complicated to compute with. And writing this reduction today in LTAX is painful because you have to keep track by hand of all the constants that you would like to unfold. So it would be nice, at the very least, if there were an easier to extend variant of compute with delta, other than just, say, peeking through your file and keeping notes of everything that you would like to reduce after having defined those functions.
So I don't understand exactly if you would like the thing to be clever and guess what needs to be unfolded or not, or you would be happy writing once and for all some unfolding rules that should be then taken into account everywhere else.
I guess I would like to have something in between, closer to the second option, meaning I would like to have an extensible database of unfoldable constants, a little bit like hint unfold, but one that could be taken into account by a custom reduction strategy. And it would be even better if this could be extended after the fact, so that in one file, it only uses some set of constants to unfold, but later on can extend this and then it will unfold even more things.
Yeah, so I would say that the extension mechanism I would use in Elpi is the one I demo before. It wouldn't be just this copy thing, but it would be a way to add the rules.
Yeah.
Like you could just say this has to be unfolded like a unary predicate that is true for all the constant that you want to unfold. But then you would need to write your own function that crawls a term and on each and every subterm decides what to do. That is something that the other reduction strategies that are already available in Coq kind of do. For example, lazy, here it takes no arguments other than the term to be reduced. If you call it from Coq, you can pass to it quite many flags.
Yeah.
Maybe there's no easy way to give a name to a set of options so that you don't have to repeat yourself over and over, but I'm not so sure that the easiest solution to your problem is to do it in Elpi, even if it would be a nice exercise, I think.
This is true. That's a fair point. I'm just wondering, because I've been struggling with this simplification problem for a while, and because the default simplification strategies are so rigid, I keep wondering if there would be any performance gains to be obtained by using clever ones that could perhaps be programmed in LP. Although I imagine those would by default perform worse than the native OCaml ones, right?
Yeah, of course, it's...
Yeah.
A similar question, Enrico. Imagine you have some transformation rules which require equality, so that you have to provide a proof of equality. So it's not just say stuff which is convertible, but stuff which is involves inequality. So is it imaginable that by LP you construct the equality proof of, so the simplified term and the equality proof?
Yeah, that is what I would do. So I would, what is it? Here copy term are just two terms. I would also add another one, let's call it proof, okay?
Okay.
That is a sort of a trace or something that can later be turned into an actual proof term. It could even be a proof term from the start, but I really don't know what you would need to record.
Yeah, well, either it is an application from, I mean, in case it is convertible, the proof term is just equal, and in case it is not convertible, it is some lemma which says that it is equal.
Yeah, that's. I would do it like this. I would then add another argument and carry it. So a rule like this one that is doing nothing would just have a proof like I was called f equal. Okay, the term that says that you can map under. And when you actually do something in your rule, then you have to provide a term.
I mean, I think about something like simplification in like machine word modulo arithmetic, where you always, I mean, where nothing is equal, and you always have to prove that modulo machine size it is equal or something like that. Interesting.
Yeah, in some sense, I would say that in your scenario, each rule you add would also have here an evidence, okay, that the rule
Yeah.
makes sense, where the evidence is something you proved. You proved in Coq, something like this.
Mm. I mean, I did similar things in MTAG2, where the nice thing is that in MTAG2 you can then write only rules where the evidence is actually correct for what you say. But I guess that would then get tricky in LP.
So in LP, LP has a type system of its own, but it's not as powerful as the one of MTAG. So it will complain if you don't pass all the arguments around, but it does not understand dependent types in some sense. So you would need, you can call the Coq type checker in debug mode to know if you're doing something silly, but it won't be done completely statically. Anyway.
Yeah, still, I mean, the ability to add rules on the fly, which especially in simplification is something which happens frequently, is a substantial advantage, I would see. Yeah. Interesting. Thanks.
Okay, so I guess there are no more questions. Last round, everybody. Here comes the time for the recap today. Once again, I'm going to pick people one by one, except if you manifest yourself. So please go ahead.